Okay, so the last time we were here, we talked about the fact that, well, we defined what enthalpy is. And enthalpy is, as we said before, the sum of the internal energy plus the pressure times volume product of a system. And we also came to the conclusion that the enthalpy change under constant pressure is actually the change in the enthalpy of the system. So let's talk about enthalpy, some key facts about enthalpy. The first thing we're going to say here is that enthalpy is an extensive system. So what does that mean? It means basically that the enthalpy of a system depends on the quantity of material that's present in the system. So you see this statement in this box here talks about 2 logs on a fire gives off twice as much heat as does 1 log, right? That's just basically to illustrate or explain what the term extensive means. Of course, we're assuming that the 2 logs have the same amount of material in them for this to be true. Another thing about enthalpy that you need to be aware of is that enthalpy is a state function because the internal energy, the pressure, and the volume are all state functions. All right? So basically, since the enthalpy is dependent on this combination or a combination of these state functions, that means that enthalpy must be a state function as well. As we said before, enthalpy changes is the same thing as the heat change under constant pressure. It turns out that for different chemical reactions, the enthalpy changes are unique, all right? Another thing we need to talk about here, and this is related to the state function statement that we made here, is that the enthalpy change depends only on the initial and final states, which is true for all state functions, all right? Okay, so some other important facts about enthalpy. We can only determine enthalpy directly by experimentation, all right? Now, in some cases, as we're going to see, we can actually calculate delta H, the change in enthalpy, for a reaction that an experiment is not done, but the other values that are used to calculate it would have to be obtained experimentally. I'm going to get into that later on when we discuss Hess's law. In terms of the sign of enthalpy changes, we talked about this earlier with respect to heat change. It's the same thing. Basically, if delta H is negative, that means that the reaction is exothermic. If delta H is positive, that means that the reaction is endothermic, and we can represent exothermic and endothermic reactions using these diagrams. So in the diagram on the left, that represents basically an exothermic reaction occurring where the energy or the enthalpy of the reactants would be greater than the enthalpy of the products. So therefore, as you go from reactants to products, there's a decrease in enthalpy, which means that delta H is negative, which means that going from the reactants to the products, heat is lost by the system. So therefore, we're talking about an exothermic reaction in that case. And the opposite is true when it comes to endothermic reaction. So here we have the reactants, which has a lower enthalpy compared to the products. So as you go from reactants to products, there's an increase in the change in enthalpy, which means it's positive, which means that the reaction is endothermic, all right? So basically, you can tell whether or not a reaction is exothermic or endothermic based on the sign associated with delta H, the change in enthalpy. Okay, so let's talk about what happens when you reverse a reaction. If the reaction is reversed, then the sign of delta H is changed, right? So if the reaction going in one direction is associated with delta H being positive, then the reverse reaction will be delta H negative. And therefore, in a cyclic process, delta H is 0, right? So if you go from reactant to product and then from product back to reactant, then delta H would be equal to 0. And that's very important when it comes to calculating delta H for certain reactions, as we're going to see later on. In fact, let's look at this example right here. So in this example, we're looking at the reaction on this side of mercury 2 oxide forming mercury and oxygen. This is the equation for the reaction, and this is an endothermic process requiring this amount of heat in order for this reaction to take place, all right? So going from the reactant to the product, in this case, involve this amount of energy, and then the reverse process would be the same in terms of magnitude, but different in terms of sign, right? So basically, if you're going from mercury 2 oxide to the products of mercury and oxygen, and then going back to mercury 2 oxide, then for that cycle, the enthalpy change would be equal to 0. Okay, so what we're going to look at here is an example based on what we have covered in this course, or in this chapter, I should say, so far. Let me get this thing working here. For some reason, my laptop here is now acting up. Anyway, in the meantime, let me try to explain, or let's go through this question. It says, given the equation, and it gives you the equation, and it gives you also, it gives you delta H value for that reaction. The question is asking for you to calculate delta H for this equation, all right? Now, the first thing I'm going to say here is that if you compare this equation to this equation, you'll notice two things, all right? You'll notice that one, the products of the equation here would be the reactant in this equation and vice versa. The reactants here would be the products of this reaction, all right? So that's the first thing you'll notice. The next thing you'll notice is that all the coefficients for the first equation right here for the different substances are halved when you get to the next equation, all right? So the question is, what will those two things, what effect would those two things have on the value of delta H given for this equation? So what I'm going to do is get out of this and then go to my writing tablet here. Let me get rid of this. And let me do something here on my other laptop here so I can monitor. Okay, this thing is acting up again. Okay, so basically, hold on. Okay, so basically, we have H2 gas plus I2 gas to give 2HI. And according to the information given here, delta H, okay, what's going on here? Okay, I'm sorry about this, folks. Let me try to deal with this quickly. My laptop, okay. So let me go down here. Okay, so delta H for this is equal to plus 52.96 kilojoules, all right? Now, as I said before, let me write down the other equation. HI gas to give half H2 gas plus half I2 gas. Whoops, let me erase this here. I2 gas, all right? And delta H for this is what the question is asking for, all right? So as I said before, when you compare this equation to this equation, you'll notice that the product of this reaction here, or product of this equation, is the reactant and vice versa, right? So what I'm going to do is turn this equation around, right? Now, if we turn this equation around, if you remember what we said before, the inverse or the reverse equation would result in the delta H sign being changed. So in this case, it's going to change from plus to minus. So 2HI gas to give H2 gas plus I2 gas will give delta H equals to minus 52.96 kilojoules. All right? And then you'll notice when you compare this equation to this equation, all the coefficients are reduced by half. So what does that mean? That means that if we divide right through by 2, this value here, delta H, would have to be divided by 2 as well, right? So HI gas to give half H2 gas would be the resulting equation when we divide all the coefficients by 2, plus half I2 gas. Delta H for that is going to be equal to minus 52.96 kilojoules divided by 2, right? So minus 52.96 divided by 2 gives you 26.48, minus 26.48, minus 26.48 kilojoules. And that would be how that is done. All right. So that's basically how we solve that particular problem. Okay. Now for the next question, going back to the PowerPoint here, the next question says, it talks about the complete combustion of liquid octane, and it gives you the formula. And it says it produces carbon dioxide and liquid water at 25 degrees Celsius. And at a constant pressure, gives off 47.9 kilojoules of heat per gram of octane. So the question is asking for you to write down a chemical equation to represent this information. Let me just say that the question is not really clear. Let me just explain what the question is asking for. The question is basically asking you to write down an expression for this reaction looking something like this. All right? In other words, you have the balanced equation, and then you have the appropriate value for delta H based on the information provided. All right? So how are we going to do this? Let me get out of this here, and let me go back to my writing tablet. Let me get rid of this here. And the first thing we need to do in order to answer a question like this is to figure out what the balanced equation is. So the question says, let me read it again. It says, you're starting off with octane. Let me write down the formula for octane. C8H18, and that's a liquid. So let me put liquid state here. And it's combusted, which means that it's going to react with oxygen from the atmosphere. And the products would be, as always, when it comes to hydrocarbons, carbon dioxide and water in this case would be in the liquid state. All right? So that's the unbalanced equation, and therefore now we have to balance it. And the way we balance it is that we put an 8 here, and for the hydrogens we put a 9 here, and then we have 8 times 2, 16, 16 and 9, that's 25 oxygens. So I would put 25 over 2 here. But of course, we need to convert this to an integer, which means that we have to multiply the entire equation by 2. So this becomes 2 times C8H18 liquid plus 25O2 gas to give 16 CO2 gas plus 18 H2O liquid. So that would be the balanced equation. And as always, I tell my students whenever they're balancing equations, do a final check through to make sure that everything is balanced. So let me do that quickly. Here, we have 16 carbons, 36 hydrogens, 18 times 2, 36 hydrogens on the right. And then we have 50 oxygens. Here we have 32 oxygens plus 18 oxygens. So that gives you 50 oxygens. So everything is balanced. So that's the first thing we needed to do in order to answer this question. The next step now is to determine the enthalpy change for this reaction. Now, how are we going to do that? Well, first thing we're going to notice, the question gives us that the reaction produces heat, and the amount of heat that is produced is 47.9 kilojoules of heat per gram of octane. Now, again, we have to pay attention to how the question is worded. It says it gives off 47.9 kilojoules of heat, which means that we need to put a negative sign here, right? So this here represents the amount of heat that is the heat change per gram of this substance right here, the octane. So what we're going to do is find out basically how much heat is generated when 2 moles of octane are used. So what we're going to do is start off with 2 moles of C8H18, right? And then we're going to multiply this by the molar mass of octane. So we're going to have 1 mole of octane here above, and down here the molar mass. Let me quickly calculate the molar mass of octane. So let me do this here. I'm using my molar mass calculator here. C8H18. Okay, so according to what I get here, the molar mass of octane is 114.23 grams per mole. So we're going to put down here 114.23 grams Oh, by the way, this is incorrect, the way I set it up. So let me correct that right now. So let me erase this here. The 114.23 should go above. So let me go back to my pen function. So it should be 114.23 grams of C8H18. And here we're going to have 1 mole of C8H18. All right. And then, so what we have calculated so far would be the grams of octane. And then here now is where this relationship comes in, where we're going to put minus 47.9 kilojoules, whoops, above as the numerator, and 1 gram of octane, C8H18, down here as the denominator, right? And then that's it, pretty much, in terms of the setup, because this is going to cancel with this. So the only unit remaining would be kilojoules. All right, so therefore, let me do the number crunching here. 2 times 114.23 times minus 47.9. And have to round this off to 3 sig figs. So according to my calculation, this works out to be equal to minus 1.09 times 10 to the 4 kilojoules. So basically the delta H value here, let me erase this here. Go back to my pen function. So the delta H value that should go here, where the delta H is right here, is minus 1.09 times 10 to the 4 kilojoules. All right? And that's basically it. So the answer, the final answer would be what I'm putting in the box right here, or what I'm circling here. That would be the final answer. All right? Okay. So that's basically how that example is done. All right, what shall we talk about next? Let's talk about delta H in stoichiometric calculations, right? Now, when it comes to solving problems involving enthalpy changes and so on, in some cases, we can conveniently represent the heat change as either reactant or product, depending on whether or not the reaction is exothermic or endothermic. So basically, if heat is produced or evolved in an exothermic reaction, then we can treat, I should say, the heat change as a product. And therefore, we can put delta H in the equation on the right side of the equation. Now, if heat is absorbed, in the case of an endothermic reaction, then we can treat the heat change as a reactant. And therefore, we can put the delta H value on the left side of the equation. All right? So in other words, let me go back to my writing tablet here. So let me remove this here. So for example, let's say we have, I'm trying to think of an example. Okay, let's say we have N2 gas plus H2 to give H2 gas to give ammonia. And to balance this, we need a 2 here, and we need a 3 here, all right? So this reaction I know to be exothermic, so delta H in this case would be less than 0, all right? I don't remember what the value is, but I know it's exothermic. So in this particular case, we can rewrite this equation. Since heat is produced, we can rewrite this equation as N2 gas plus 3H2 gas to give 2NH3 gas plus the value of delta H. We can treat delta H as a product because in this particular case, the enthalpy change is negative. Heat is produced, so therefore we can put the value of delta H here on the right. So this is what happens in an exothermic reaction. Now, in the case of an endothermic reaction, let me think of an example. Okay, here's one example of an endothermic reaction. Let's say you have PCl5 forming PCl3 plus Cl2. Again, I don't remember what the value is, but I know that delta H for this is positive, all right? So in this particular case, because delta H is positive, we can rewrite this equation as PCl5 plus delta H to give PCl3 plus Cl2. And that's because heat is absorbed, delta H is positive, heat is absorbed, which means that this reaction is endothermic, which means that we can write delta H in this equation, or the value of delta H in this equation, we can place it on the left side of the equation. All right, so sometimes it's useful for us to do that so that we can do the appropriate calculations. Okay, let me go back to the PowerPoint here. So, here's another example. We can, well, not another example, but we can generate conversion factors based on the balance equation involving delta H. So here's the example that we're going to use to illustrate how we can generate conversion factors. So in this particular case, we have H2 plus Cl2 to give 2HCl. So that's a balanced equation, and this is the corresponding delta H value for that reaction, right? So what this equation is telling you, right, is that for every 1 mole of hydrogen that reacts with 1 mole of chlorine, it produces 2 moles of hydrogen chloride, and the enthalpy change, given those amounts, the enthalpy change for that reaction would be minus 184.6 kilojoules. So we can represent relationships between the amounts of these substances and delta H as what we see here. So for example, in this case here, we are establishing the relationship as a conversion factor between the enthalpy change of the reaction and the moles of hydrogen, or we can do the same thing with the enthalpy change and the moles of chlorine, and we can do the same thing as far as the enthalpy change and the moles of HCl. So here we have the enthalpy change value and 2 moles of HCl because we have a coefficient of 2 in front of the HCl in the balance equation. And that also can be useful when it comes to doing certain calculations, as we're going to see shortly. All right? Okay, so let's look at this example. The question says, what is the enthalpy change associated with, hold on 1 minute here. What's the enthalpy change associated with the formation of 5.67 moles of HCl in this reaction? So it gives you the balance equation and it gives you the moles of HCl. So what I'm going to do again is get out of this, go back to my writing pad here. Okay, so the equation given is H2 gas plus Cl2 gas to give 2HCl gas, and delta H, according to the question, is equal to minus 184.6 kilojoules. And the question gives you the moles of HCl, 5.67 moles of HCl, and the question is asking for, based on this, what is the delta H value in, presumably in kilojoules, for this amount of HCl. So what I would do in this case is start off with the given moles of HCl, and I will multiply that by a conversion factor which reflects the relationship between the moles of HCl and the enthalpy change, right? So in this case, I'll put 2 moles of HCl down here, and up here I'll put minus 184.6 kilojoules above as a numerator. This goes with that, and then you do your number crunching, which is what I'm going to do right now. 5.67 times minus 184.6 divided by 2. So according to my calculation, the answer when rounded off to 3 sig figs is going to be equal to minus 523. Minus 523 kilojoules. And that would be the amount of enthalpy change associated with this amount of HCl based on the balance equation. All right? Okay, so we're going to stop here. And the next topic we're going to talk about is how do we measure enthalpy changes. In other words, we'll be dealing with calorimetry. Calorimetry is basically what we use in order to take measurements or calculate measurements of enthalpy changes for chemical reactions. All right.